these problems. 47 is actually much nicer with the work energy equation than if you tried to do this otherwise. Let me show you real quick here. All right, 47. Determine the elastic potential energy, so it's PES. Now, the thing about this course is sometimes they're a little careful to call it change versus not change. Sometimes they're sloppy. So basically, PES and delta PES are going to be more or less the same in this course. Like I said, you go in a higher level course, it's not true. But anyway, a spring that is stretched 2 meters by an average force. So stretch is X is 2 meters by an average force of 25 newtons. You can call that force on the spring if you'd like. Okay, now if I'm running my PES equation, PES is 1/2 kx squared. I'm like, all right. So first I have to go figure out k. Except for those of you who really want to worry about this one, not a common question, beware that this Fs equals kx, this is the F, force on the spring, final, not average. And I'm telling you, in this course, you will most likely survive just fine without this. The final force on a spring is actually twice the average force on the spring. And you can pull that from this graph, Fs versus X. We did a lab like this. You stretch out a spring, you get a relationship looks like that. So the average force on the spring is somewhere here in the middle, like this. However, the final force on the spring is here. This equation calls for the Fs, calls for the final. The equation that I am more concerned with for this problem, being that they gave us average force, is the connection here. Oh, PES. Man, is there another way to go about this? Answer, why, yes, there is. Here it is. It is the work on the spring, which is FSX, which fits our givens perfectly. FSX, there's our givens, and you will get your work on the spring, which is the PES, a much quicker way to go about the problem. Even 48 is another one like this. So I'm going to start to shorten up my explanation of them. Just give you a quick 1-2 on this business. How much work must be done to bring a bike to rest? So this is work done to accelerate, which, by the way, is the same thing as the net work. That's our question mark. Of course, your equation is most likely going to be, as you knew it from before, F net D. But maybe your givens don't match that. Like the mass of the bike is 20 kilograms, and the bike is traveling at 20 meters per second, and it goes to rest. Notice this is like, so we don't have to worry about the weird equation. It always starts or ends at rest. Not weird, but higher level equation. Makes it easy. F net D doesn't match our givens. What does match our givens? Oh, work to accelerate just so happens to be the delta KE, which just so happens to be 1/2 mv squared. By the way, for those of you who really are interested in the detailed equation really is, I'll put in parentheses over here, 1/2 m vf squared minus vi squared. And notice the vf is 0, so this kind of disappears right here. And it makes sense that the answer would be, it's negative vi squared, the answer come out negative, because it does, the ke decreases. The PES one up here also, in case you want that full version, it's really 1/2 k x final squared minus x initial squared. Sorry, if you don't have audio here, you're not going to know what I'm writing. All right, so you don't have to worry about those in this course. But so that's how this process works. Basically, this provides us another way, an easier way to go about doing these problems. Here's a great one. Heck, I can't stop. Sorry. How much does the internal energy increase? They're asking for delta Q. You don't even have an equation for delta Q. Oh, but now you do. You know it's the work done against friction. And that you know is FF, or done by friction, FF D. So does that fit what we got here? Ooh, this is a slippery one, isn't it? Rough but slippery. Okay. A 1 Newton copper block, that's FG, is 1 Newton. Little throwback here. It's copper on steel. Oh, oddly particular. It's sliding, so you get the kinetic coefficient of friction. I hope my memory serves me. I believe that one was point. Ooh, copper on steel. I might be messing this one up. I was going to say 0.57. Then I wanted to say 0.36. Maybe it's 0.36. Anyway, I'll fill that in a second. Let me think about it. It'll come back to me at some point. Okay, so let's keep going here. They want to know, displacement here, 3 meters. So can we actually get this FFD? Sure we can. Here's the block. Here's your FG. Here's your FN. Since it's on flat ground, this FG and this FN are going to be the same. Okay, and we're back. Yeah, this is a kid use iPad, so limit some of that time. Midnight just hit. Anyway, copper on steel, yeah, that was the 0.36. Not a 0.57. I was thinking of steel on steel. Good. Hope they let us blend these two videos. Okay, so 0.36. And here, if you notice, the friction is going to be off to the side. Solve for your friction with the coefficient, the MeFN. So 0.36 times 1 is just, 0.36. And then that times D. 0.36 times 30 is going to be a little over 1, and that'll do it. All right, so you see how this process works? It's really kind of a nice thing. It's nothing new here. There's no magic here. We're just kind of putting together the disparate pieces of work and energy. Now we can connect them and say, you know what? It's all kind of playing the same game. How do you speed things up? Well, force changes the energy, slow things down. So this energy-force connection, or energy-work connection, is deep. Okay, let me just set you up on this one in case you want to think about it. The box is pushed from rest. The distance of D is 6 meters. Pushed from rest, VI is 0. The force that's your external force, 20 newtons. This friction does, so work of friction is 40 joules. Determine the object's final kinetic energy. So we're going to find KE is question mark. And so notice here, always chase the question mark given. The truth is, I don't even have it in my mind right now exactly how this problem is going to do. And that's what makes it powerful. If you just say, all right, KE is 1/2 mv squared, that's what I want. And then you're like, well, I don't know the mass. And I don't know the speed. So maybe that's not the best way to do this. Maybe I can do this with work. Work done to accelerate, which would be F net D. Do I know anything here that will help me with that? Oh, well, we know D, so that's good. And we need F net. And you know what? They're talking forces, so don't mess around. Put yourself a little diagram over here. There it is. And so you got your FG, you got your FN. Those are going to cancel out. You've got a push, and you've got a friction. Now, you already know the work done by friction is 40. And the push, well, we have a force of 20 newtons over, let's see here, 6 meters. So that's 20 times 6. So this external work over here is going to be, there would be F external times D, 120 joules. And so you got a couple ways to look at this. First, you can look at the works. Actually, I kind of like this here. We have room to write it. We got a little room down here. Let's use it down here. You could do this as the net work is going to be, well, these two works are going differently, so external work minus work done in friction. And in this case, the net work would be then, what was that, 120 joules minus 40, 80 joules done. The other way is to do this with forces, so you could actually get the force of friction here. You know that the external is 20, so if you did this with forces, F external minus FF will give you F net. F external, you know, is 20. FF, you would actually have to do, let's see, you got the work, do that FFD. So 40 divided by 6, which is 6 2/3. Let's say 6.7. And so the F net over here is going to be about, what's that, 13.3. And then you would have to multiply that by the 6 meters to get it in the end. And 13.3 times 6, let's see, 1360, yes, 78, and then a third of 6 is 80. Works perfectly. Either way you do it. More than one way to skin that cat. Finally, there's some graphs over here, and these are pretty straightforward. Basically, this is just forcing the relationship, it's just encouraging the relationship between PES and the WS, WG, PEG, WS, PES, KE, F net. So right away, WG, PEG, they're the same thing. The slope here, actually, since they're literally the same thing, the slope is 1. It's a nice trick one. Not trick, but interesting one. WS, PES are literally the same thing. Slope is 1. W to accelerate and delta KE are the same thing. Slope is 1. WF and delta Q, same thing. Slope is 1. And then these, KE is W net. So really, which is F net D. So it's Y equals X times 1. And the slope here is just D. It's KE over F net. Same thing over here. The slope is just going to be X. Okay. I know there's a lot of stuff written there, but the truth is when you do your actual problems on W7-9, you will see there's not much trickery to this. It's just recognize that in addition to your energy equations, you have a work version that connects. In addition to your work equations, you have an energy version that connects. All right.